Hello everyone, welcome to lecture 49 in the course Diffusion in Solids. So, this week we have started talking about diffusion in classes of materials which are important for various technological applications and understanding. So, today we are going to look at some of the aspects of diffusion in metallic alloys. And we will continue this in the next video also after or the first video of the next week as well. So, this is about the metallic alloys. So, today we are going to talk about some of the things or features of the self diffusion in metals and the interstitial diffusion in metals. So, let us start. So, first, remember that till now we have already covered some of the general or the fundamental concepts. Now, what we are going to see is sometimes some empirical relations or trying to understand the correlations between various types of materials or sometimes the metals with different structure with similar structure. Is there a correlation between their diffusion coefficients and so on. So, this is more about understanding the trends in the diffusivities in these metals and alloys. So, for example, here I have put the self diffusion data for the FCC metals. So, some of these FCC metals copper, silver, gold, nickel, palladium, platinum, lead, and you will see that here is the delta H and D naught. These are the references from which it is taken. And what is also calculated here is delta H by Kb into Tm. So, this is what is known as the normalized activation enthalpy. And if you notice that more or less it follows a similar regime except lead, which is on the slightly higher side. So, and you see, so therefore, if you talk about the FCC metals, the diffusivities near the melting temperature are similar for most of the FCC metals, and they lie in the range of 10 power minus 12 to 10 power minus 13 meter square per second. PB is exception because of much lower diffusivities. That is why I also pointed it out in the previous slide that it has a higher activation enthalpy. And on the homologous temperature, if you see the diffusivities for most of the FCC metals except lead lie within a narrow band. So, all the FCC metals the diffusivities do not vary so much. And we already know this Arrhenius relation, D is equal to D naught exponential minus Q by RT. And if you start seeing the activation enthalpy for FCC metals lies in the range of 15 to 19 kbtm. So, this is what was shown in this table also. So, you can see that most of the FCC metals except lead the diffusivity lies in this range. And the diffusion entropy is 1 to 5 kb, and the pre-exponential factors are from 10 power minus 6 to 10 power minus 4 meter square per second. And even the pre-exponential terms, I mean in the D naught, the pre-exponential terms all have a very similar value up to 10 power minus 6 meter square per second. So, most of the FCC metals, if you compare on the homologous temperature scale, the diffusivities are within a narrow band. Remember, this homologous temperature scale is important because many times, so for example, if you take certain elements, for example, copper and nickel. Now, copper melting point is 1000 degrees, 1063, whereas nickel melts somewhere around 1400. So, if you start comparing the diffusivities at 900 absolute temperature, you may see that the copper actually is diffusing faster because it is very close to its homologous temperature, the vacancy concentrations are high and so on. But so close to its melting temperature. So, that is why it is better to compare, or in the diffusion literature you will see that always the comparisons are made at the homologous temperature scale. So, that is why we say that we talk about this delta H by kbtm, or we talk about the diffusivities at the melting point when when we are comparing the various elements or elements which have same structure, or sometimes FCC, BCC and so on. So, one more trend that people see, that within one column of the periodic table, the diffusivities in the homologous temperature scale are the lowest for the lightest element, and they are highest for the heaviest element. For example, in the noble metals group, gold self-diffusion is fastest and copper is slowest. In the nickel group, palladium, platinum self-diffusion is the fastest and nickel is the slowest. Again, if you see the data, this trend is reflected in the enthalpy values also. Nickel has the highest activation enthalpy and has hence the lowest diffusivities among the nickel group vertically. So, in the BCC metals, for example, so this is a schematic for the original figures, you can refer to this reference. And if you see the BCC metals, usually in BCC metals the spread is more. That means FCC metals, we say that the diffusivities, if you compare on a homologous temperature scale, they lie in very narrow band. Whereas for the FCC metals, the diffusivities are more spread across. So, we will see this as well. So, first of all, the diffusivities for BCC metals at the melting temperature are slightly higher than the FCC ones. So, they are in the range of 10 power minus 11 to 10 power minus 12 meters per square per second. This is often attributed to the open structure of the BCC. Then you have a wider spectrum of self-diffusivity for BCC metals than FCC. For example, if you compare at 0.5 Tm, then the difference in diffusivities at melting point for sodium and chromium is about 10 power 6 meter square per second. Whereas for the FCC metals, gold and nickel, it is 10 power 3 meter square per second. So, you have a much wider spread than in the case of FCC. And if you compare within the BCC metals, self-diffusion is slowest for the group 6 transition elements like chromium, molybdenum, tungsten, and fastest for the alkali metals like lithium, sodium and potassium. And here Arrhenius plot of some BCC metals shows convex curvature which is slight deviation at higher temperatures. And again within one column of the periodic table, here also like FCC, the diffusivity at homologous temperature scale is lowest for the lightest element and highest for the heaviest element. Then we already have seen this a little bit, that in the case of metals, the self-diffusion proceeds by the vacancy mechanism predominantly. And in the vacancy mechanism also, the dominant contribution comes from the mono vacancies till 2/3 Tm temperature. The mono vacancy contribution is the most dominant one. You start getting the die vacancy contribution at higher temperatures. So, we have seen that D star when one vacancy is involved can be written like this, where the concentration of or the equilibrium concentration of vacancies is given by exponential minus delta G F for mono vacancies by kBT. And this omega is nothing but the jump exchange rates which is given by the Debye frequency multiplied by the free energy term, the free energy of the migration. So, you have both formation as well as migration coming into picture. Then which can be further expanded into delta S and delta H, and we have seen that the activation energy Q is equal to delta H formation plus delta H migration. Same goes for the diffusion entropy also. And because it is a vacancy mechanism, so correlation factors do come into picture. So, you have for FCC it is 0.781, for BCC it is 0.727. Now, when both mono vacancy and die vacancy contributions are present, so the diffusivity is the total of the diffusivity caused due to the mono vacancies or diffusivities of the die vacancies, and therefore, you can now write separately the activation parameters for both. In the case of the die vacancy, the enthalpy of die vacancy formation, the total delta H2V is given by this term 2 times delta H1VF minus H2VB plus H2VM. So, this is the delta H2VB is the binding enthalpy and delta H2VM is the migration enthalpy. So, remember now here in the case of die vacancy there is also a negative term. Okay. So, that means when the two vacancies come together the bonds are being formed. So, therefore, it is a gain in energy for the systems or it is rather lowering of the energy of the system. So, that is favorable, that is why it enters as a negative term. You do not have to supply that energy basically. Whereas this term indicates that first two vacancies have to be formed, the mono vacancies have to be formed, then there is a certain energy which the system gains by binding of these two vacancies, and then there is a migration enthalpy term which also goes into the delta H2V, which is the enthalpy or the activation energy for the diffusion. Similarly, for the entropy of diffusion, delta S2V is also given by similar expression, where you have a binding entropy contribution and a migration entropy contribution. And when you write the D naught, here now the tracer correlation factor is die vacancy tracer correlation factor. So, this is just to give you some data for the self diffusion of silver. The D naught is this, and delta H is 1.76 electron volt for the mono vacancies. Delta D naught for die vacancy is 10 power minus 4 meters square per second, 2.2. Enthalpy of activation energy for die vacancy is slightly higher than the mono vacancy. So, it is 2.24 electron volt. When you have both the mechanisms operative, then the effective delta H can be written as delta H mono vacancy into D star 1V by D star 1V plus D star 2V plus delta H 2V into D2V star divided by D1V star D2V star. Same thing for the activation volume which accounts the pressure dependence also can be written. Usually the delta V for mono vacancy is less than the delta V for die vacancy, and since the die vacancy contribution is higher at higher temperatures, so the effective volume increases with increasing temperature. Studies have been also done to measure the isotope effect parameters, and here the isotope effect parameter E effective also shows a similar behavior. You have E1 V into D star 1V divided by D star 1V plus D star 2V plus E2 V into D star 2V divided by D1 V star plus D2V star. Then let us come to some features of the self diffusion in HCP and tetragonal metal. So, we we indicated this earlier when we were talking about the Fick's second law or Fick's first law, that there are two principal components of diffusion coefficient in the case of uniaxial materials like HCP and tetragonal. So, the D perpendicular and the D parallel. So, one is the diffusivity perpendicular to the axis and D parallel to the axis. So, for zinc, let us say the D parallel is higher, the D star refers to the tracer diffusivity, parallel is higher, whereas for indium and tin the D parallel is lower than the D perpendicular. For these metals, the anisotropy ratio is rather small, that means you have in the range of 1/2 to 2. The diffusivity of these elements zinc, cadmium, Mg at the melting point is roughly about 10 power minus 2, 12 meters square per second, which is closely related to the FCC structures, which is not surprising because HCP also is a close pack structure like the FCC. BCC ones we saw are slightly higher because of the open structure. So, when you have the vacancy mediated diffusion, then each of these diffusion coefficient can be represented as a square by 2 CV equilibrium 3 omega A into FA perpendicular plus omega B into FB perpendicular. So, you have two types of, so you see that in this case also, when you talk about HCP metals, let us say, when you talk about perpendicular to the C axis. So, remember perpendicular to the C axis is the basal plane here. Now, you have vacancy mediated diffusion. So, omega A is you can see the exchange along this direction, omega B is exchange along this direction. So, therefore, there are two different types of frequencies that come into picture. And when you talk about the parallel diffusivities, there is only one that is needed, which is omega B, but you have a FB parallel. So, you have three correlation factors, which are FA perpendicular, FB perpendicular and FB parallel. And then the concentration of vacancies also come into picture here. So, as I said, vacancy atom exchange rates within the basal plane and vacancy atom exchange rates oblique to the basal plane. So, I hope it is clear that it is this gray atom is not the one in the basal plane, it is at a angle. So, this is the omega B we are talking about, because diffusion will happen by exchanges here and by exchanges here and by exchanges here. Okay. So, the anisotropy ratio, if you calculate d star by d star perpendicular by d star parallel, then using the relation mentioned in the previous slide, also you can write it as 2 a by 3 a square by c square 3 omega a FA perpendicular plus omega B FB perpendicular by omega B FB parallel. If you neglect the correlation effects, that means A is equal to 2 by 3 A square by C square 3 omega A by omega B plus 1. There are certain metals where the phase transitions take place, and how the diffusivity is changed there. So, the most classic example is the iron, where iron alpha, although iron shows the allotropic transitions, iron also shows a magnetic transition. So, alpha iron to gamma iron, it is a first order transition, the temperatures are indicated here, and this transformation leads to the decrease in the diffusivity. That means, if you compare just below the transformation temperature, just above the transformation temperature, you will see a jump in the diffusivity because of the change of the structure. And FCC being the closest close packed structures, or more close packed structure than BCC, you will see a decrease in the diffusivity values. On the magnetic transformation, when iron changes from magnetic to ferromagnetic to paramagnetic, then this is a second order transition, and it is also accompanied by the difference decreasing the diffusivity. So, the paramagnetic iron will show a lower diffusivity, although in this case the change is not as high as what you see in when the crystal structure itself is changing. So, people try to quantify this change by fitting or putting some model like d star is equal to dp naught exponential minus delta hp 1 plus alpha h square by kbt. This is the paramagnetic phase, and S is the ferromagnetic order parameter. So, which is given by the ratio of spontaneous magnetization at temperature T and at 0, and alpha is a fitting parameter. Phase transition is also, we know, is shown by certain other elements like group 4 transition elements, which are titanium, zirconium, hafnium. All of them have room temperature structure, which is HCP, and high temperature structure, which is BCC. And here again, if you compare the diffusivity is just below this transformation and above this transformation, the change of crystal structure from HCP to BCC actually leads to increase in diffusivity by nearly 3 orders of magnitude. So, this is again because of the crystal structure changes. Then let us spend a few minutes on seeing some of the trends in the diffusion of interstitial solutes in metals, which are again very important. These occupy the interstitial sites of the host lattice and diffuse much faster than the atoms of the host lattice or the substitutional solutes, because the sizes of these interstitials are very small. And because no defect is necessary to mediate these jumps, no defect formation terms enters the expression for diffusion coefficient, and no defect formation enthalpy contributes to the overall enthalpy of the diffusion, and that is why the enthalpy is lower, and these atoms are able to move fast. So, here is an example of interstitial diffusants in niobium. Carbon, nitrogen and oxygen. So, you can see the wide difference in the activation energy. So, oxygen, carbon, nitrogen, nitrogen is 161, which is the highest, but niobium self-diffusivity, the activation energy is 395, which is nearly more than the double. So, D naught also lies in this range. So, therefore, interstitial solutes we know are very fast diffusers. Now, what are the experimental methods to measure diffusion, this interstitial diffusion? Why we are just pointing out these methods here, although we have talked about the experimental techniques before, is to what experimental techniques out of those we have talked about are suitable to measure interstitial diffusion in metals. Okay. So, for example, you have some steady state methods which are appropriate for fast diffusers as carbon, nitrogen and oxygen. So, you have to develop a steady state concentration gradient which can be directly measured or calculated from solubility data, and then you have to measure the flux using either a gas flow method or electrochemical cell. So, you have to design an experiment such that there is a steady state diffusion, and by measuring the flux and the concentration gradient and by the appropriate Fick's law, you can calculate the diffusivities. Then radio tracer method, so carbon 14 isotope can be used. Stable isotopes, so oxygen and nitrogen usually by radio tracer are not possible. So, but you have enriched stable isotopes, so that you can use use the technique of secondary ion mass spectrometry to study the oxygen and nitrogen diffusion. Then diffusion couple methods, out diffusion methods, in diffusion experiments. These are some of the more methods, sometimes not as much as the previous two are used for calculating the diffusivities of these interstitial elements. Then among the indirect methods, Snowick effect, internal friction methods, and sometimes magnetic relaxation methods also have been used to study the diffusion of carbon, nitrogen and oxygen. Then we also saw this when we were talking about the mechanism. So, when you have the dilute alloys, the interstitial diffusion, when it takes place, it also only has the term migration and migration terms into picture, because if it is a dilute alloys, that you have the probability that it will always find a site vacant or interstitial site vacant near to it, and therefore you have only the migration terms, no defect formation terms comes into picture. And for the jumps between neighboring octahedral site, this, for example, this geometric factor is 1 for FCC, for BCC it is 1/6, and the D naught usually lies in the range of 10 power minus 7 to 10 power minus 4 meter square per second. And we know that the correlation factor is 1 for the interstitial diffusion. Then about hydrogen diffusion in metals. So, hydrogen it forms an interstitial solid solution with most of the metallic elements. Some metals have a negative enthalpy of solution and high solubility for hydrogen. These forms hydrides at higher hydrogen concentrations. Some of the metals have positive enthalpy of solution and relatively low solubility like iron, cobalt, nickel, etc. As you may expect, the hydrogen diffusion occurs very fast in metals which is even observable at room temperatures. Just to give an example, hydrogen in niobium has a room temperature diffusivity of about 10 power minus 9 meter square per second, which corresponds to about 10 power 12 jumps per second. So, this is extremely fast at the room temperature. The smallest activation enthalpies and largest isotope effects have been found for the metal hydrogen systems. So, this diffusivity, what we mean by metal hydrogen system is diffusion of hydrogen in the metals. So, some amount of quantum effects are also involved in diffusion of hydrogen because hydrogen has a small mass. The three isotopes of hydrogen, hydrogen, deuterium and tritium, they have large mass ratios, and therefore, the isotope effects can be studied over a wide range, sometimes which can give us important insights into the diffusion mechanisms. So, here are the tabulated data. So, you can see, for example, the delta H for hydrogen is 0.14, whereas for the deuterium it is 0.163 in tantalum. If you compare niobium, then again it is 0.068 or 0.106 in niobium for hydrogen diffusion. For deuterium it is 0.129, for tritium it is similar, like 0.125. So, the isotope effects have been measured in the hydrogen diffusion, and this is more prominent than some of the other elements where the isotope effects are studied. So, the diffusion of hydrogen, why is important, and particularly in systems like iron, for example, because in steel it is a technical challenge, the hydrogen embrittlement. The diffusion of hydrogen causes an embrittlement in iron and steels, and the absolute values of hydrogen diffusion in iron actually are very high. They are higher than those for palladium and nickel. And what also happens is, when people try to measure hydrogen diffusion in iron particularly, there is a lot of scatter in the data because of various reasons like surface effects, then impurity trap the hydrogen, then dislocation, grain boundaries or precipitates, they also trap hydrogen, and then you have formation of molecular hydrogen in micropores, either already existing in the material or produced when you have excess loading. So, all these factors make difficult the reliable determination of hydrogen diffusion. That is why you see a large scatter in the data. Hydrogen in niobium also has been studied in a wide temperature regime, and because of the high diffusivities, and the diffusivities because it does not change very significantly with temperature for hydrogen. The Gauss-Key technique, which we saw as an indirect method, could also be used for hydrogen and deuterium in the very wide temperature regime. Remember that when we talked about Gauss-Key technique, it is useful for a higher temperature range and hydrogen diffusion in metals. For BCC metals, usually, so we talked about the isotope effect, and this isotope effect for BCC metals, hydrogen enthalpy is lower than the enthalpy for deuterium. This is what we saw in the table for niobium, tantalum. For FCC metals, the delta H or the activation enthalpy of diffusion for hydrogen is more than for the deuterium. So, we are not going into the exact reasons for that, but just to give you certain trends for hydrogen diffusion. So, with this we will end today's discussion on the hydrogen or on the diffusion in metallic alloys. We will continue in the next video.